Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Siemens EDA with Russ Klein. I'm going to talk today about software-defined systems. Russ, there seems to be a push toward software-defined everything these days. What are you finding as some of the problems, what's changing, and how do you see this evolving going forward?
Software is easy to create. There's a huge body of open source tools and IP that's out there that people can build on. And software is incredibly flexible. People can build a system and they can deploy it to systems. And if they need to fix it, they can download new versions over the air, even while the systems are deployed out in the field. So it's absolutely wonderful to be able to create these systems that are completely software defined.
So what sort of problems do you run into as you get into software-defined systems, though?
One of the really big challenges is, can we take all of the functionality that needs to be embodied in your embedded system and have it all implemented as software? As these systems get more and more complex, they're starting to strain the capability of embedded processors, which means sometimes we've got to look at, do we need to augment these systems to be able to reach our performance and efficiency goals, especially in the embedded system space?
Well, let's take a closer look at how we get there.
Sure.
Russ, what are we looking at?
What we've got here is a graph that shows the performance of compute capability across time. Now, Moore's law states that we're going to get more and more transistors, and the electronics industry has been able to support that. And even moving forward, we're going to be going down to 5 nanometers, 3 nanometers, 2 nanometers. That continues unabated. But we haven't been able to translate this into compute capability on the processors. If we look at single-threaded performance, what we're seeing is that that's becoming almost flat. We're not seeing the increases in compute capability for general-purpose computers anymore. This is a result of the end-of-Dennard scaling, power density issues, as well as the memory wall, getting data into CPUs and back out. And in the face of all of this, systems are continuing to see increased demands for compute capability. If we look at 5G to 6G, we're going to need to process a lot more data on networks. If we look at image processing, we've got more pixels, faster frame rates, and all of these systems are going to start to do inferencing, which brings on a huge amount of computational complexity.
So what are engineers going to do about this?
Well, there's a number of different approaches that can be taken. Dave Patterson knows a bit about this. He's the vice chair of the RISC-V architecture. He created the MIPS architecture. He's well known in the computer architecture space, literally wrote the book that most of us studied in college. His thesis is that we need to go to domain-specific architectures. And what he means by this is take a modest base compute capability, and rather than trying to add the ability in that CPU to do general purpose computing well, augment it with acceleration that will do very specific functions that your system needs to do to enhance that processing capability, so that we can continue along delivering the capability more along Moore's law than along what we've done on general purpose compute so far.
Another piece of this is that we can no longer fit it into the size of a reticle. So we do need to start adding this outside as well, which is why we're starting to see all this advanced packaging. What's the implications of that here?
Indeed, the ability to go to chiplets and take these accelerators, which could get quite large as they're processing things like convolutions or matrix multiplies or tensor processing, those can now be placed in packages that are off the initial die and still be able to deliver a lot of additional compute capability, offloading the processor.
So how does an engineer actually create one of these domain-specific architectures? It's a different way of looking at the problem, right?
It really is. What you'd start with is taking your entire body of software, that software-defined thing that you want to deploy, and profiling it on the processor family that you're trying to send this out on. That's going to enable you to find where the bottlenecks and where the heavy computational loads are. You probably already know where that is by instinct, but understanding exactly where it is will let you know how much potential speed up you can get by turning that into an accelerator. Once you've done that, the next step is figuring out the data flow between the body of software and the accelerator that you're about to create, and mapping out some strategies for that data movement. Then, of course, you've got to create the accelerator itself, and that's a hardware design process. And then integrating that back into the main processing architecture. And then we've got to get software integrated as well. It's a challenge.
It's also an iterative process too, right? So you need some sort of fast results in order to be able to say, here's what's going to work, or we think it will go to work, is going to work. How does this work with the other pieces that are going into this design?
Indeed. So doing this sort of the old-fashioned way of sitting down and doing an RTL implementation of these accelerators, where the engineer is mapping out every wire, every register, every operator, is really not practical in this flow. Now, the good thing is that your implementation from your software-defined system is probably going to be in C, C++, maybe Python, maybe Rust. High-level synthesis tools take as input C and C++, and many of them are moving to take in Python as well. So the most popular embedded languages can be used as input to the high-level synthesis process. The high-level synthesis process can then create synthesizable RTL. Now, this is still a hardware design process. The engineer is still going to think about data movement, parallelism, pipelining, all of those aspects of the deployment in the RTL. But the thing that you want to know very quickly is what's the impact of this accelerator on the overall system that I'm building. Now, in an RTL process, you learn what that is very, very late in the design process. With high-level synthesis, we can tell you almost immediately what the estimated power, performance, and area are going to be very early on.
This is a very different path from where HLS started out. For the first 10, 15 years of its life, nobody knew quite how to use it, right?
Well, high-level synthesis is still used by hardware developers to be more productive, to create designs faster, and to go through verification faster. But this is another application of that same technology, and it fits very well because that software-defined system has an input which high-level synthesis can take, and we can also generate the interfaces. So in addition to generating the accelerator block, we can do what's called interface synthesis, create the hardware bus interfaces, as well as the software interfaces necessary to integrate the accelerator into the larger system.
And what you're looking at here is three different elements, right? You've got the hardware itself, how that behaves. You've got how fast it moves data back and forth to memory. And also you've got the software side of this as well, which all has to be integrated with this.
Indeed. So it's not just a hardware design process. It's really a hardware design process, an integration process, and then an overall programming challenge. And all of these need to work and play well together.
So where do engineers run into trouble with this?
One of the things that happens when we create an accelerator is we're introducing new data paths between the original processing element in software and the accelerator. Now, the accelerator is going to go much, much faster than software will. It brings in a lot more parallelism, and there's a lot less data movement. The challenge that you've got, though, is you've just introduced this new data path, and you need to be able to structure that communication in a way that it doesn't negate all of that performance benefit that you get from doing the processing faster. So it's critical to understand the data movement and the impact of moving that data on the overall throughput of the system. There are times when we can connect the accelerator through a coprocessor interface to have it very tightly coupled to the processor. Other times we want it on the main bus so it can take advantage of the bandwidth out to different memory elements. We can also take those accelerators and have them cache coherent with the processor complex. And this also minimizes the data movement. But again, we've got to be able to measure those things early on and understand, are we getting the gains necessary to deploy this system?
So is a lot of this theoretical, or are people actually working with us today?
Actually, we've got customers that are taking advantage of this today, being able to build systems where they can use more modest processors, which are much more energy and area efficient, by creating these accelerators. And they're moving functions from their body of software into these hardware accelerators using high-level synthesis to reduce that development time rather dramatically. We also have examples that we can show you of different systems that we have created, which include encryption, data compression, as well as inferencing systems, including a wait word.
And you can play off of this in any way you want. You can improve performance, you can improve power, you can even improve area as well too, right?
Indeed. As an engineer, you're really working with these trade-offs of, do I need it to go really fast and I don't care about area or power, or do I need it to be really efficient and I'm not that concerned about performance? This gives you the ability to hit that right combination of power, performance, and area.
And after that, all the normal engineering work begins, right?
Then you've got the real work in front of you. Exactly.
Russ Klein, thanks for a great explanation.
Thank you.